Acids and bases are the important part of chemistry. One of the most applicable theories is the Lewis acid-base motif that extends the definition of an acid and base beyond H plus and OH minus ions as described by the Bronsted-Lowry acids and bases. So the bronze acid-base theory has been used throughout the history of the acid and base chemistry. However, this theory is very restrictive and focuses primarily on acids and bases acting as the proton donors and acceptors. Sometimes conditions arise where the theory does not necessarily fit, such as in solids and gases. So in 1923, G.N. Lewis from UC Berkeley proposed an alternative theory to describe acids and bases. His theory gave a generalized explanation of acids and bases based on the structure and bonding. Through the use of the Lewis definition of acids and bases, chemists are now able to predict a wider variety of acid-base reactions. Lewis' theory used electrons instead of proton transfer and specifically stated that an acid is a species that accepts an electron pair while a base donates an electron pair. Lewis acids accept an electron pair. Lewis acids are electrophilic, meaning that they are electron attracting, while the Lewis bases donate an electron pair. They are the nucleophilic, meaning that they attack a positive charge with their lone pair. The reaction of Lewis acid and Lewis base will produce a coordinate covalent bond. A coordinate covalent bond is just a type of covalent bond in which one reactant gives its electron pair to another reactant. In this case, the Lewis base donates its electrons to the Lewis acid. When they do react this way, the resulting product is called an addition compound, or more commonly, an adduct. So now let's talk about the Lewis structures. In many instances, only the valence electrons, also called the outer shell electrons or bonding electrons, are interest in chemists. In such cases, it is advantageous to draw the Lewis structure of the atom or molecule. In a Lewis structure, the entire atom, with the exception of the valence electrons, is represented by the symbol of the element, and the valence electrons are represented by dots. So there are many reactions involving the Lewis acids and bases. So let's take a look at this example. So the curved arrow shows the direction that electrons travel. A new bond is formed. And can you identify why each Lewis acid can accept electrons? So in the first reaction, like this boron trifluoride, which is the BF3, can accept a pair of electrons because boron has an incomplete octet, or just 6 electrons. Remember, boron is one of those exceptions to the octet rule. So the product or the adduct of this reaction is tetrafluoroborate, which is the BF4. In the second reaction, hydrogen ion, or H+, is a cation that can accept a pair of electrons from ammonia, NH3. The product formed is the ammonium ion, which is the NH4+. Let's go now with our example, and always remember that the Lewis acid electron pair acceptor, while the Lewis base electron pair donor. So let's try to look at the example of this acid-base reaction. The Lewis acid-base theory can also be used to explain why nonmetal oxides such as the CO2 dissolve in water to form acids, such as carbonic acid, which is the H2CO3. So this example, CO2 plus the H2O yields to form H2CO3. In the course of this reaction, the water molecule acts as an electron pair donor, which is the H2O, or our Lewis base. The electron pair acceptor is the carbon atom in CO2. When the carbon atom picks up a pair of electrons from the water molecule, it no longer needs to form double bonds with both of the other oxygen's atoms as shown in this figure.